Alrighty, so let's start. So basically, so did you get this? So this is actually very important. Now what we will do, we did everything as we always do, right? Remember, we did the income effect, substitution effect graphically. So we know what they are. And here we, got all these curves. Also, we derived these curves graphically as well, right? And then we draw these guys on the graph. Now we're going to go back to math, okay? So we were missing our derivatives. So now we're going to get these guys. You'll see the relationship between these guys and such, using derivatives, okay? So you'll see using math. So let me actually, I think I can erase this part because I might need our pictures. But now we're going to get this, as I said, these guys using some mathematical tools. Okay, so you'll see the link. So there is actually an easy way to get this compensated or Hicksian demand curve, and which is this. If I give you the expenditure function, you can take the derivative of the expenditure function, and then the derivative of the expenditure function will be Hicksian demand, okay? So let me write this down, and there is a special name for this. It's called Shepard's lemma, okay? Why? Because a guy named Shepard found it, okay? So it's called Shepard's lemma. So let's write this. Shepard's lemma, okay? And then due to R.W. Shepard, and he basically said this. When you take the derivative of the expenditure function, okay, with respect to price, you are going to get the compensated demand curve. You can call either U bar or U. It means that for a given utility level, okay? So this is basically the case. And why? Why this is the case? Now, you might think of it, right? What was the expenditure function? You were solving the expenditure minimization problem, which was something like this, right? Px times x plus py times y, right? And it was xy. And then subject to some utility level, right? That you want to keep fixed. So this was the expenditure minimization problem, right? Or I can write it like this. Minus u equals to 0, or u bar minus this equals to 0. It doesn't matter, okay? And how are we solving this? How are we solving these problems? We were using Lagrangian, right? So we were writing it's Lagrangian, and it was px times x, py times y, plus a lambda, right? You can say u of xy minus u bar, or I think I wrote it u bar minus u of xy, because it's a problem of equality constraints, it doesn't matter, okay? If it were a problem of inequality constraints with the Kuhn-Tuckers and such, it would, okay? But here it wouldn't. So it's so this is basically the case. So this is the Lagrangian. So how do we get the expenditure function? I solve this problem. I'm going to get my xc and yc from here. I plug them back into this function, and then my expenditure function was something like this. Remember? Px times xc, py times yc. You can see why, when I take the derivative of the expenditure function with respect to px, it's actually giving me xc. But you know that in math, things are not that, that easy. So we have to show this, okay? So how are we going to show this? You'll see. We're going to, have you heard anything called the envelope theorem? Who are my engineer students? Do we have any students from the engineering department? So not there. They're not here today. Okay. So it's. Have you heard? Probably they haven't seen it either. Have you heard anything called the envelope theorem? Envelope. Yes, we all have heard envelope, right? But the theorem. So this is. It's okay, but I'll actually write it down. So it's called So don't forget that these guys are what we call parameters, okay? Remember, I told you that I'm going to give you prices. I'm going to give you utility, okay? I'm going to give you the prices. I'm going to give you the utility. So these are given to you. These are not determined within the model, but these are actually given to you, okay? So just keep that in mind that these are parameters. So let me give you recall. Of course, if you don't know, you cannot recall. So, okay, envelope theorem, okay? So, envelope theorem. So, suppose you have a problem like this. So, you see that things are very similar in math compared to our case. So, basically, you would like to minimize this, okay, x1, x2, xn, a, okay? So suppose you would like to minimize this function, and these are the ones that you would like to, you want to minimize them with respect to these guys, and a is a parameter, okay? So you'll see that it's going to be, for instance, look at this. You want to minimize this with respect to x and y, and these guys are parameters, okay? So here a is not a scalar, but a parameter. If you want, it's a parameter vector, okay? It's consisting of all these parameters, alpha, beta, theta, gamma, whatever, okay? Here in our case, px, py, u. So subject to, right? Suppose you have, again, your constraint, which is equal to 0. Mostly math problems are, right, constraints are written like this. That's why I wrote it like that, okay? Equals to 0. Now, if I want to find this optimal x1 star, it's going to be a function of what? In this case, remember, I'm going to solve for optimal x1 star, x2 star, xn star. So these guys will be a function of, that's why I said that. Check this out. Here, so from here, xc is a function of what? Px, py, and u bar. So these optimal guys are functions of a, right? The parameters, px, py, u. Right here, we call them in this, math form, I call this a. Okay, it's a vector. So you see that these guys will be a function of these parameters, okay? x1, a, x2 star, a, okay? xn star, a. If I want to get the value function, which we said, remember, so the minimal value of f, then what I do is that, remember, I plug them in. So this is going to be f of x1 star a, x2 star a, dot, dot, dot, right? So let's call this y star. So this is the minimal value of function f. Okay, and then this is going to be xn star a. Okay, so the minimal value of this function, which is y star, is actually a function of all these, right, guys, whatever these functional forms, and also but the parameters, right? That's what we know, the expenditure function. This is a function of all the parameters. This is a function of all the parameters, right? Now, so this is the case. Suppose I'm interested in this guy. Or suppose, if you want, you can call a scalar, or let's say one of these, a parameter vector, ai, whatever, okay? With respect to one of them, okay? So it's, so you can say a, it's a vector, a1, a2, dot, dot, dot, I don't know, ak, okay? So it's a parameter vector, whatever, okay? But suppose I'm interested in this derivative. And for the time being, assume that there is one parameter, okay? That a is just, there is, for instance, px. Does this look familiar? What is y star? For instance, if you think of this, what is my y star? It's the minimal value function is, so look at here. So it's very similar, right? So my y is this guy, right? So this is my y. This is my constraint, my g here, right? So this guy is my g here, right? And then when I get these optimal points, I plug them back into this one, and that's going to be my y star. My y star is what? It's the expenditure function, right? Because it's remember the function, the value function. So px, py, u. My y star. So you see that actually the envelope theorem is answering our question. What is this derivative? What is this derivative? Envelope theorem. It's like, what is the derivative of y star, which is the expenditure function, with respect to, one of the parameters, let's say px. Okay? So if you want to figure out this, let's put it, if you want to figure out this derivative, okay, so what is the problem? Why can't you say immediately, you take the derivative with respect to px, why can't you say immediately xc? Why not? Because suppose I would forget about this, I'm taking this guy's derivative with respect to px, right? So you say that there is px here, but you would say, hocam, this xc is a function of px, py, u bar. There is a px here as well. And in this guy, px, py, u bar, there is a px here as well. So I should take into account, remember the chain rule, when I'm taking the derivatives, I should be, taking all these derivatives, right? That's why it was smart to say xc, right? Oh, hocam, it's very easy. Look at this. You write this. The derivative of this with respect to xc. Right? But there's good news. Because these are optimal points, envelope theorem tells us that you can ignore, that px's contribution, that ai's contribution to the optimal points. And then say that it's xc, okay? So let me write this down. Just keep this in your mind, and it's going to be pretty, as your friend was saying, havalı olur. You say that, we learned envelope theorem, right? So it's going to be, pretty impressive, right? So but let's write this down. But basically, you understood where we are going to use it, right? So to get the Shepard's lemma, and basically this is this. So envelope theorem actually says if you have this derivative, if you want to take this derivative, it says that form the Lagrangian, take the derivative of your Lagrangian with respect to ai first, and then ignore the fact that these guys are coming also depending on a, okay, on these parameters. Then evaluate this derivative at the optimal points. This is what envelope theorem says, or let's put it like this. So evaluate this at these points, x2 star, xn star, okay? So basically, it is the case. And then let's put it like this, okay? Just to make sure that, okay? So this is what envelope theorem says. Take the partial derivative of the Lagrangian with respect to ai, right? The whatever, px, for instance, take the derivative of the expenditure function with respect to px, which is xc, and then evaluate it actually, which is this, right? The function that you would like to minimize right here. Take the derivative of this guy with respect to px, which is x, and then instead of x, put the optimal point. Okay, that's what the envelope theorem says. So basically, this is the case. So you see that you can ignore the effect that is coming through these optimal values. Okay, so let me write this down. I'm not going to erase that guy, but so let's do this here. So we are interested in this derivative, px, py, u, del px, okay? Apparently what I can do, I can write down the Lagrangian. My Lagrangian was something like this, px times x plus py times y plus lambda u of xy minus u bar. My Lagrangian was this. So it tells me that envelope theorem says that take the derivative of this Lagrangian with respect to px. Okay, I will. And then evaluate this guy as x is equal to xc, right, which is the optimal point, and y is equal to yc, px, py, u bar, okay? And then this is going to be, so what is the derivative of this Lagrangian with respect to px? X, right? So it's x, and then apparently you need to compute it as x is equal to xc, y is equal to yc, and then this comes px, py, u bar. You see how easy that was, but we needed math. If we know the envelope theorem, then actually we can get this. Okay, so you can all call it y. This is again an informal way of proving it, but this is the case. So from now on, if I give you the expenditure function, you can take the derivative of that expenditure function with respect to px and get xc. If I take the derivative with respect to py, I'll get yc, right? So it wasn't a tricky question, right? So if I take the derivative with respect to py, I'm going to get yc, okay? So this is basically the case. Okay, now, remember I wrote down all these stuff and that was for a reason. Remember, so let me again keep these guys. Did you write this part? Yazdınız mı burayı? Okay, so then we can get rid of envelope theorem, okay? But you see it's cool, right? Isn't it cool that it helps us a lot? Yes.
In that box, x of c, and then there's u, but then there's u constant.
Oh, no, I put this u bar as this level, yeah, okay? So it means that it's for a given level of u. If you want, I can keep it as u or I can keep it as u bar. But you are right. So she's saying that, hocam, there is no u bar. I can put here u bar or I can put here as u. Okay, but you know that it's actually constant. Okay. So now let's do this. Let's have a look at this. Now we will actually. Okay, so. No, not me. No pizza. Yeah, so I doubt it will come, but we'll see. So it's remember when I write down the properties of the expenditure function, I said that expenditure function is concave in prices, right? So remember we said something like this. This expenditure function is basically, or if you want, I can call it u, okay, or u bar, whatever you want. So we basically said that this is negative, right? In our previous class, we said that expenditure function is concave in prices, right? So recall that expenditure function is concave in prices. That's what we said, right? Now let me write this derivative like this. Del, okay, and then let me have del expenditure function, u, del px, and then I'm going to take this guy's derivative again with respect to px, okay? And I know that this is negative. What is this? Now we learned from Shepard's lemma. What is this guy? Right, so it's compensated demand for x, right? So this guy is equal to xc, px, py, u, okay? So now, then what does this mean? It means that the derivative of xc, px, py, u with respect to px is always negative. What is this? The derivative of xc and del px. What is it? This is, how do we call this? What is it? It's a slope. It's the slope of compensated demand curve, right? So it's the slope, right? So if this is my compensated demand curve, I take, remember, it's this. This is my compensated demand curve. If I take the derivative of this guy with respect to this guy, it's going to be actually, okay, so here is the thing. The one that I keep drawing here is called, this is not exactly the demand curve, but this is actually what we call the inverse demand curve, okay? Because you see that here I'm putting Px, and it's going to give me xc. Remember, I told you it was due to Alfred Marshall. The real, like if you want to plot it, you should put x here and px here, right? Because px is the one which is changing, right? It's the parameter which changes, and then we know what's going to happen to the quantity of x that you would like to consume, right? So basically, it's going to be, right? So you can, the real demand curve, you should write x here and px here. The one that we plot here is called inverse demand curve. And that's why the slope of the demand curve would be given as, for instance, here, with this. But what is the slope of this line here, or curve here? It's actually this, right? Right? If you want to check the slope of this curve is, right, so the change in the y-axis divided by the change in the x-axis. So the slope of that curve is this. But the slope of the demand curve is actually this. But it doesn't matter, right? As long as it's continuous, you can actually flip it, right? Take the inverse of it. But just keep this in your mind that this is actually the one that we plot here is the inverse demand curve. But don't worry about it, okay? So that's why the slope is going to be 1 over the other guy. Now, okay, coming back to here, this is the slope of the compensated demand curve. Apparently, the slope of the compensated demand curve is always negative, right? I mean 0 or negative, right? But did we say the same thing about this guy? What was this? So remember, px, py, and? It's me? No. No food. No food, right? I, right? So this is, do we know that this is always negative? Can I say this? Remember what we learned in our previous class. We said that derivative could be, when was it positive? Remember for which goods? We learned Giffens, right? So remember, Giffen goods were these weird goods. Remember, we said the Irish potato, rice in the rural regions of China, whatever. And in these cases, we had a demand curve like this. When price increases, consumption of that good was also increasing. Okay? So it was remember, for Giffen goods, this was the case. Right? So you see that for ordinary demand curve, for Marshallian demand curve, for uncompensated demand curve, I cannot guarantee that it's always going to be downward sloping. Here, for the compensated demand curve, I can guarantee that it's going to be always downward sloping. And this is also linked to something else that we have seen. Remember, what did you say? So it was Essen. Right? Yes. So, okay, good. So you see, I managed to say it. So correctly, hopefully, right? So you see that you told me in first class, you told me that, hocam, on the compensated demand curve, there is only the substitution effect. And we said that what substitution effect is always, from here, we actually get that substitution effect is always negative, right? Meaning that it's always negative in the sense that when price increases, it's going to tell you to decrease the quantity. When price decreases, it's going to tell you to increase the quantity. So this derivative is always negative. So substitution effect is always negative, but apparently, but here, remember, there were both of them. Apparently, which could make this positive is what? Is income effect, right? And when income effect is really big, it dominates the substitution effect, which is always negative. It dominates the substitution effect, and in the end, it might make this total effect positive for the given goods, okay? Now, we'll see this via math. So there was this guy, another smart guy, okay? So I don't know whether I should still keep these, but not Shepherd. But this time it's going to be some Russian guy called Slutsky, okay? I think Eugen Slutsky. So he figured this out. So let's write this down. So now this is, remember here we said that at what point, at this point, right, we said what? Both in that one and in this one. So I'll show you. So in these, remember both of these cases. So here we have the uncompensated demand curve, the ordinary demand curve. Here we have the compensated demand curve. And here we have actually, right, so we said that at this point E2, what do we have? We have X star, right, is equivalent to, we said X double star is equal to X double star C, right? Because at this point, income is just enough to get this utility level. So the compensated demand curve, right, and the basically uncompensated demand curve, they're going to only at that point, they're going to give you the same number, basically. But as you keep changing, suppose price changes a little bit, then things will change, right? Price increases, then we know that this compensated, remember how we draw this? So this was steeper, so the other guy is going to be flatter, so something like this, right? Only at this point they're going to give you the same number at px prime, but when price changes, then these start to get apart from each other, okay? Now in math, of course, we like the fact that they're equal to each other at some point, and then we will make use of that fact, okay? And this is going to lead us to what we call the Slutsky equation, okay? But here is what Slutsky did, so you can do it as well. He actually looked at this, he said that, oh, okay, so for this, suppose for this U bar level, okay? So for this, let's say when prices are Px, Py, and when you have this level of U bar, so this is your compensated, this is your optimal X, right, to reach that optimal level U bar. And you found the minimal amount of expenditure. You give that amount as an income to the consumer, and you know that the consumer is going to get this maximal utility level U bar, right? So we know that they're equal to each other at that point. So let's call this X star, Px, Py, and instead of I, okay? Artık sana sonra, başka zaman, tamam. So it's a, thank you. So it's a, you see that, for instance, for I know that this I is equivalent to Px, Py, U bar, right? So it's the minimal amount of expenditure I need to make in order to reach the utility level U bar, right? So remember, these guys were all inverses of each other, right? So now, instead of I, because of that, I'm going to write that guy. So let's do this. So this is basically Px, Py, and U bar, okay? Now I'm going to take derivatives of both sides with respect to Px, okay? So you'll see. Now let's take the partial derivative with respect to Px. So this is going to be del xc del Px, which is equal to what? So let's take this guy's derivative with respect to Px. You guys tell me. Of course, but don't forget that you see that I'm taking the derivative with respect to Px, but it should be, right, around this small neighborhood. Remember, derivative is this incremental change. It's not a huge change. We know that when there's a huge change, these guys are not equal to each other, right? So basically, I have this. So what is the derivative? So let's take it together. What is it? So let's write this. First, Px appears here, right? So that's why we said del x star del Px. And then Px appears here, right? And remember, so we say plus. So let's actually call this guy was I, right? So you can actually say del expenditure, right? I'm going to take, I'm going to del X star, del E, right? And then I'm going to have del E over del PX. So do you guys know some stuff here? Do you have familiar stuff? What is this? We just learned. What is this guy? Neydi expenditure fonksiyonunun PX'e göre türevi? Huh? Eksi, right? So you know that it's the compensated demand. No, don't worry. I mean, you guys know all this stuff. So this is eksi, right? And then I can actually, I know that this guy is equivalent to my income, okay? And then I can write all these guys like this. X star PX plus del X star del I, and then XC, okay? And then I have this guy here. Now, let me actually rearrange stuff here. Del XC del PX minus, right, del X star del I times XC, okay? Now, you're going to see this equation is very important because remember in our substitution effect and income effect graph, what did I do there? I said that, okay, price of X changes. How much this is going to cause, suppose price of X increases, you are going to decrease your X star, right? If it's a normal good and such. And then we said that, well, how much you're going to decrease your consumption of X, we call that total effect, right? So you see this guy here is the total effect. And then we try to decompose it into two. We said there is substitution effect and we said there is income effect, right? So which one do you think is showing us the substitution effect? Right, the first one, because what is this? It is the slope of the compensated demand curve, and we know that on the compensated demand curve, there is no income effect, right? So we compensate the individual for changes in price, exactly, for actually in the real income, right? So so when price changes, I know that what happens here, when price increases, for instance, I give this guy a little bit of extra money so that he can be on his same utility level, on the same well-being level, right? And then I look at how much he's going to decrease his consumption. That's why you see that this guy is going to it's going to give us the substitution effect, okay? And this guy, don't forget that with the minus sign here, so let's put it like this. This part here, because you always get confused with that. This part here is the income effect, right? So this is substitution effect, and this is going to be income effect, okay? With the minus sign, okay? And what do we know about this derivative? You see now, whatever we have learned, they're now all going to make some sense. We said that this derivative is always negative, right? So you see that substitution effect is always, so this guy here is always negative, okay? What about this guy? So here. So this is, remember that it has a negative in front. So altogether it's the income effect. So let's see. So you see that, so this is positive. Okay, so it's like amount, suppose you consume either zero or in positive amounts, right? So we don't allow you to consume in negative amounts. What about this guy? What is this? When income changes, how much how does your demand, remember those derivatives that we were curious about? Is this always positive? No, right? You said that hocam. Ne oldu?
Yok ben negatif diyordum, pozitif diyordum da.
So you're both right? İkiniz de haklısınız. So this is, remember, this guy is actually positive if normal. This guy is actually negative if inferior. So you see what's going on. If it is normal good, positive, positive, but there's a minus sign, so income effect is negative, right? So it's going to work in the same direction as the substitution effect. If it's a normal good, when price increases, substitution tells you decrease less of that good. Income effect tells you you're poorer, consume less of that good, okay? If that is a normal good. But you see, if the good is an inferior good, positive, negative, negative, altogether income effect is positive, right? Negative, negative, this guy is positive. Altogether, income effect is positive. Then substitution, price of X increases, substitution effect tells you decrease your consumption. But price decreases, you feel poorer, but it's an inferior good. Income effect tells you consume more of it, right? Substitution effect tells you to decrease it. Income effect tells you to increase it. Do we know what's going to happen to the total effect? If its income effect is dominant, it's positive and it's greater than the substitution effect. This effect is going to be positive. It's going to give us this inferior good, which is given. If income effect is positive but cannot dominate, is not as large as the substitution effect, even if it's inferior, you would still have, PX increases, decrease your consumption, okay? So you see that this is very important. So this is what Slutsky figured out, but you see we proved it, so we don't need Slutsky, but he was the, first guy who figured this out.
Demand curve'le aynı şey, slope'un inverse değil mi?
No, this is the total effect. So you see, this is the slope of which demand curve? Uncompensated, yes, so that's what you said, right? Yes, so he's right. So this total effect, because in the compensated demand curve, there is only this, substitution effect, that's it. We only have its slope. There is no income effect there.
Aynı şeyler.
Huh?
Aynı şeyler. Onun eğimiyle o total effect dediğimiz şey.
Yes, exactly. Okay? So because it's basically what we mean by when you increase the price, how much you're going to change your consumption. Okay? So that's the slope of that demand curve, and the total effect is going to be the same, okay? How you would move when Px changes, so it's basically this. You see, it's the slope. When I change Px, for instance, from here to here, you move from here to here, so when this changes, this guy changes how much, right? So it's the slope, okay? So your friend was asking, what was your name? Talha. So Talha is saying that, hocam, so is this the same as the slope of the uncompensated Marshallian demand curve? Yes. Okay. So let me write this down in a nice way. The Slutsky guys. Okay, Slutsky did it in a, so you're going to see that in his formulation he also uses X star because they're equal to each other, like to begin with. So let me write it, and then I'm going to write down the Slutsky equation, and then so let me write this down. Basically, so let's write this. Okay, so it's called Slutsky equation. So you're going to see that when we solve problems before the exam in the review session, and please remind me that I'm going to assign some problems from the book, okay? So that you guys start practicing. So please don't leave everything on the last 1 or 2 days. This is micro. You might get everything, but you might get, during the exam, then you're going to get stuck, and maybe you have heard I give exams as booklets. So I have lots of, problems. So it's going to be long, okay? So it's going to be 2.5 hours and such. You need a fresh mind. So if you went to bed really late the night before, then sometimes it happens, students know, but during the exam they cannot do anything, okay? So make sure that you started practicing earlier. That's why I'm going to have 2 review sessions. Don't worry, we're going to have enough, like we're going to solve enough problems, okay? So don't worry, I'll do and I'm available. You can come and ask me anytime you want, but just keep that in your mind, okay? So when we solve those problems in review session, you're going to see that, for instance, mathematically, we're going to solve the, let's say, Cobb-Douglas utility maximization, blah, blah. We're going to get everything. And then I'm going to ask you to show me actually the substitution effect, the income effect, and you're going to get these guys, okay? You'll see, it's not going to be hard. Once you have the expressions for x star and xc star, you can get these guys, okay? But you'll see. So don't worry, we're going to solve problems, okay? So Slutsky equation, as I said that, Slutsky, he actually wrote this, so he figured this out, and then we can, once we do this, and then we can stop. So this is basically, so he did this, okay? This is his kind of original formulation. So I'll write this, but know this, okay? Just with the little twist that I'm going to write instead of this, x star, okay? That's it. So px, pyi, del px. You see that this is weird. This is not as we write this. That's why I wanted to give you this guy first. But he wrote it like this. So basically it means, the same. It means that you're changing px, you're looking at the optimal x consumption, but you're keeping the utility level the same, okay? So you see that, but this is not a very good way of writing it, right? So we have this xc. That's why I wrote it like that. But this is, how he wrote this stuff. And then minus, he wrote x star px pyi times del x star px pyi divided by del I, okay? So he wrote this. So basically this corresponds to del x star del px is equivalent to del xc over del px. So this guy is that, okay? Minus, so basically del x star del I times x star, okay? So here is how we get it, as I said that. This is the Slutsky equation, okay? So just use this one. But as you know where that comes from. And it's just that we know that because they're equal to each other to begin with, for small changes in px, so they will be equal to each other. So that's actually the Slutsky equation, okay? So now, let me write it properly here, that we are going to have, so as we said that this guy is always negative, so we know that substitution effect, okay, is always negative. It works in a negative direction with px, right? So it's going to be px increases, this decreases, px decreases, this increases, right? And then remember, so this portion was income effect. So this portion, we said it depends, right? So we said, so you can actually write this. This guy is positive, but here we actually say income effect. So here we don't know. Income effect, right? So basically, if it's here, we know that if it's a normal good, we know that income effect, so this guy, if it's a normal good, this guy is positive, positive, positive. If it's a normal good, so it's going to be negative, right? Income effect. And if it's an inferior good, we said that it's going to be, right, income effect is positive because this guy is going to be positive. Okay? Oh, sorry, this guy is going to be negative. When income increases, you decrease this good. Ekmek arası patates kızartması, right? French fry sandwich. So negative, negative. So overall, it would become positive. Okay? And here we call this the total effect. You see, in the compensated demand curve, you only have this guy, substitution effect, but in the regular demand curve, ordinary demand curve, you have both of these guys, okay? So basically it is the case. Is this clear, right? So you see that now we have seen income effect, substitution effect, both on a graph, mathematically, you know, like now expenditure minimization, utility maximization. So you guys know all the links between these demand curves, all the links between, actually as Talha was saying, that all the links between the slopes of these demand curves, okay? So you know all of these guys, okay? So that's, let me not keep you any longer, but I'll call them. They should be here. Okay, so let me call